In this video, we are going to talk about linear transformations. This is the overview slide of the material in this video. We will do something like spend 5 minutes to discuss this overview slide, and then we'll go through each topic in more detail with more examples. In previous videos, we had looked at this matrix equation ax equals b, and we said that this could represent a system of linear equations, or it could represent a linear combination of the column vectors of A. In this video, we're going to look at the matrix A as a transformation that takes a vector x and produces a vector b. So if A is an m by n matrix, it takes a vector in Rn and transforms it into a vector in Rm. In this way, the equation ax equals b amounts to finding all the vectors x in Rn that are transformed to the vector b in Rm. And we can also think of this ax as a function that takes one vector and then maps it into another. And this way we'll define a transformation. We can also call that a function or a mapping. A transformation T from Rn to Rm as a rule that assigns to each vector x in Rn a vector T of x in Rm. The set Rn is called the domain of T, and Rm is called the codomain. We often see this notation T is a transformation from Rn, and the arrow, meaning it goes to Rm, indicates that the domain of T is Rn and the codomain is Rm. And if x is in Rn, then T of x in Rm is called the image of x, and the set of all images is called the range of x. In this video, we are going to look exclusively at matrix transformations. That is, our transformation can be represented by a matrix A, where A is an m by n matrix. And we want to note that the domain of T is Rn, when A is m by n, and the codomain is Rm. The range of T is a set of all linear combinations of the columns of A. So transformations that can be represented by a matrix are linear transformations. So we define what it is to be a linear transformation. So a transformation or mapping T is linear if 1, T of u plus v is equal to the sum of T of u plus T of v for all vectors u and v in the domain of T. 2, T of c of u, where c is a scalar, we can pull the scalar out, so it's equal to c times T of u for all scalar c and u in the domain of T. So every matrix transformation is a linear transformation, as I had mentioned. If a transformation can be represented by a matrix A, then it is linear. Because we have seen this when we talked about matrices in an earlier video, we saw that a matrix A of u plus v is equal to AU plus AV, and A of CU is equal to C times AU. And we'll also look at this later in this video. A couple of other notes about linear transformations. T of the zero vector is always equal to the zero vector, and T of the scalar c times vector u plus the scalar d times the vector v is equal to c t of u plus d t of v. So we often use this to prove linearity instead of proving these two steps. And then last, we can generalize this. Instead of just taking two vectors, we could have T of C1 V1 plus C2 V2 up to CP VP is equal to C1 T of V1 plus C2 T of V2 up to CP TV. And engineering, this statement here is known as the superposition principle. Whenever an input is expressed as a linear combination of signals, the system response is the same linear combination of the responses of the individual signals. Last, these are examples we were going to go through in the video, but they're important examples as they show what a projection from R3 to R2 would look like, so from R3 into a plane. It also shows what a rotation would look like. It shows a shear transformation, which you might be familiar with when you distort different images in Photoshop or something similar. We have a dilation and contraction transformation, as well as reflection across the x-axis. So these are important. They're kind of some basic transformations that you can use as building blocks for more complicated transformations later on. And because in my last slide, those examples of basic linear transformations were kind of scrunched up at the bottom because I was determined to get my overview on one page, I did go ahead and make the second page, which has my basic transformations listed out in a more reasonable size. Now that we've concluded our overview, we'll go back and talk about linear transformations and the other topics in more detail with more examples. We're looking at this equation, ax equals b. In previous videos, first, we saw that this here could be the augmented matrix, and then it can represent this system of linear equations. I kind of wrote a few key things, including the solution here. We also said it could represent a system of vector equations. So if A, using this augmented matrix here, or actually using the coefficient matrix here, we'll use the column vectors as A1, A2, and A3, and then we have the scalars x1, x2, x3, then equals B, where B is this solution vector here. So what we end up with is this matrix. This augmented matrix now becomes a linear combination of the three column vectors of the coefficient matrix. So our first vector, column vector times x1 plus our second column vector times x2 plus our third column vector times x3 is equal to b, our 0, 8, 10. So now what we're asking is there a linear combination of these three vectors, these three column vectors, that give us b? We also saw this is just plain a matrix equation. So the matrix A times x gives us b, and in this case, you can verify it has a solution as the system of linear equations or linear combinations. They all have the same solution. So if you do our matrix times vector multiplication, you'll see you get b. Last, in this video now, we're going to look at this ax equals b as a mapping. So here we have A, and it takes a vector x and it transforms it into this other vector here, where it takes the first coordinate of x, it combines it with -2 times the second coordinate, and then combines that with x3. This gives us our first new coordinate. The second new coordinate will be 2x2 minus 8x3, and the last coordinate is 5x1 plus 0x2 minus 5x3. And again, we can think of putting this vector then, where is our vector? Our x1, x2, x3, which we solved for here. Our 1, 0, minus 1 into A. So A times our vector x will give us our vector b. So now we're going to view this ax equals b as a mapping. We're going to look at the m by n matrix A. So A is m by n. And remember, it's rows, columns. So m rows, n columns. So for A equal 2 by 3, that's 2 rows, 3 columns. And this first indice on my A's, that tells me what row. The second indice tells me what column. So this is first row, first column. First row, second column is A12. A13 is first row, third column. A22, that's second row, second column. So if I'm looking at this, when I do my matrix vector multiplication, this row here gets multiplied by my vector, which means my x must have 3 entries in it so that I can do that dot product, the A11 x1, the A12 x2, and the A13 x3. So here, this is why my domain then is Rn. It's taking vectors in Rn, and then what you see is you're going to get, in this case, my A11 times x1, A12 times x2, A13 x3 is my first coordinate, and my second coordinate is A21 times x1, A22 times x2, and A23 times x3. In other words, I'm going to get something in Rm. Remember, this is m by n, 2 by 3, so Rn, this is 3-dimensional. My ending is 2-dimensional. I often get that confused when I just look at this in m by n, so drawing a little picture often helps me. So again, A is an m by n matrix, so it's going to take vectors in Rn and map them into Rm. From this point of view, solving the equation Ax equals b, so now here is my matrix A, here is my vector x, and here is the solution that I want b, which can give us this next statement. From this point of view, solving the equation ax equals b amounts to finding all the vectors x in Rn that are transformed to b in Rm. So that's what our problem is here. So the correspondence from x to ax is a function from one set of vectors to another. In this example, we're mapping vectors in R3 to vectors in R2. And I have this lovely picture. We have x in two-dimensional space, and we put it onto some point on a plane in three-dimensional space. From this point of view, the transform, sometimes often referred to as a function, I often use the word mapping. So the transform or mapping t from Rn to Rm is a rule that assigns to each vector in Rn a vector t of x in Rm. The set Rn is called the domain of t, where the things you plug into your function. Much like the notation you used in algebra in, 6th grade. Rm is called the codomain. The notation t goes from Rn to Rm indicates the domain of t is Rn and the codomain is Rm. And for x in Rn, t of x in Rm is called the image of x. So here we have x, it gets mapped to this vector here. Whatever it's mapped to is called the image. And the set of all images is called the range of t. It's what gets hit, so to speak, by the transform or the mapping. The idea of a transform is a general one, and what we are going to look at in this video is specifically transforms that can be represented as a matrix, or in other words, matrix transformations. So I copied the note on matrix transformations here so I would have more room. So t of a vector x is computed as a matrix A times x, where A is an m by n matrix, and we want to note the domain of t is Rn when A is m by n, and the codomain is Rm. The range of t, or the vectors in Rm that have something in Rn mapped to it, is a set of all linear combinations of the columns of A. And we can see that clearly when we write Ax as the column vectors of A times x. In other words, we have the linear equation form of this matrix equation, and then we said that Ax is equal to b. So in other words, the linear combination of the columns of A, that's this part here, is equal to b, and that's exactly what this says. The range of t is a set of all linear combinations of the columns of A. Our first example has A equals what is m? M is rows, so 3 by 2 matrix, 1, 3, minus 1, minus 3, 5, 7. U is equal to the vector 2 minus 1, B is equal to the vector 3, 2, minus 5, and C is equal to the vector 3, 2, 5. And T is a transformation from R2 to R3, and we see that M is equal to 3, N is equal to 2, and T of x is equal to AX. And I believe this was written out for you. I don't remember if this was given as part of the problem in your book, but either way, I've written it out. AX, so again, we're going from R2, so that's going to look like a two-dimensional vector, or two-coordinate vector, times A, and to multiply a matrix times a vector, we multiply row by column, so we have 1x1 minus 3x2, 3x1 plus 5x2, and minus 1x1 plus 7x2. So this is our three-dimensional vector, our R3 vector that gets transformed, that this R2 vector gets transformed into. There are 4 questions to answer. First, find t of u, the image of u under the transformation of t. Second, find x in R2 whose image under t is b. Third, is there more than one vector x whose image under t is b? And D, determine if C is in the range of the transformation t. The first one is fairly straightforward. T of u, we're going to plug in u. So we have t is represented by our matrix A, 1, 3, minus 1, minus 3, 5, 7, times u, which is 2 minus 1. So multiplying, we get the 1 times 2 minus 3 minus 1. Then we have 3 times 2 plus 5 times minus 1. Then we have this row times the column. minus 1 times 2 plus 7 times minus 1. So here we add and we get 5, 1, negative 9. The second question, find x in R2 whose image under T is B. Here's our vector B. So in other words, when we have our transformation Tx equals B, we want to find the x that gives us B. So I put in my A matrix, and then I have my x that we're trying to find, and then I plug in my B matrix. So we're solving this matrix equation. And we know how to do that using the augmented matrix. We row reduce it, and what that tells us then is that x2 is equal to minus 1/2, and x1 is equal to 3 plus 3x2, which is equal to 3/2. So here is my vector x, which is minus 1/2, 3/2. And this just, begs to be checked. So you can check it by plugging in A, plug in your answer, which I wrote incorrectly here. Actually, I wrote it incorrectly here, so let me change this one. It's 3/2 minus 1/2. You do the multiplication, and you get 325, which is exactly B. I left our work for part B up because it's useful in doing part C, which is there more than one vector x whose image under T is equal to B? So to do that, we're going to look at how we found our solution x. So remember, for linear equations, either there's no solution, one unique solution, or infinitely many solutions. To have infinitely many solutions, we would need a free variable, which we don't have. And we know that no solution is not a possibility because we did find one, which must mean that we are left with one unique solution. So since there are no free variables, x equals 3/2 minus 1/2 is the unique solution. So this line here is my answer, not necessarily what's in parentheses underneath. The last question, determine if the vector c, which is given over here, 3, 2, 5, is in the range of the transformation t. In other words, is there some x that will get mapped to c? And I wrote that here. Is there a vector x such that t of x is equal to c? That would put c in the range, which is the same as asking the question, does ax equals c have solution? Before I give you the answer to this question, I do want to point out that you may have noticed that for almost every question, we have a matrix and we row reduce it, and then we find x. That's almost without fail. So that part, is going to come, or probably will come. So the tricky part of linear algebra is you are learning all these different ways of viewing this ax equals b, and what you want to know is when you look at the question here, how does that relate to your equation ax equals b, and are you going to use the vector form, are you going to use the matrix form, are you going to view it as a transformation, and how does the vocabulary of transformation translate to these matrix equations and vector equations? So this is kind of the important part, is coming up with this, basically you're answering, does ax equals c have solution? And as I said, from there you come up with your matrix equation, ax equals c. So you come up with your augmented matrix, you row reduce, and you find at the very end that 0 times x2 will have to equal 5/2. So 0 times x2 equals 5/2. But there's no x2 that can make this equation true, other than, no, not even 0 makes it true. Nothing will make it true. So there's absolutely no solution, and therefore c, the vector c, is not in the range of t. This next example is one of the basic kind of transformations that you want to be familiar with. The one where you have zeros, except along the diagonal you have some ones. And in particular, this one here, this matrix here, projects points in R3 onto the x1, x2 plane. To see a little more what's going on, I am going to plug in a random x, x1, x2, x3, and I'm going to multiply it by my a, and I see I get x1, x2, 0. So every vector that I plug in, every vector from R3, every three-dimensional vector, I'm always going to get a 0, basically because of this row here, right? It multiplies 0 times x1, 0 times x2, 0 times x3 to give you the bottom coordinate. it zeroes out your x3 coordinate. And then because of the ones on the diagonal, you're also left with your x1 and x2 that are untouched. I thought I would plug some numbers in for x to see what my resulting vector would be, and then I could plot it on here just to see what, kind of get a visual picture of what's going on. So I put 1, 2, 3 through the transformation, and again it kind of left 1 and 2, the first two coordinates untouched, and then the last coordinate was zeroed out. So I'm going to plot my 1, 2, 3. So I go along the x-axis around 1 unit, y-axis 2 units. So kind of making my kind of parallelogram here. So this is the point 1, 2, 0. Actually, this is the point that ends after the transformation, but the point I put in before is 1, 2, 3. It's up here. So what happens is you have this point in 3 space, and what the transformation does is it pulls it down into the xy plane. Over here, I chose the point 0, 0, 2. I wanted to see what happens when you have something in x3. Well, it leaves the first two coordinates untouched, and the last coordinate gets zeroed out. So let's look at that. We'll do this in blue. So 0, 0, this is where we are in the xy plane, and then we go up 2 units. So here is my point 0, 0, 2. And what you can see is it gets pulled down to 0, 0, 0. Okay, so again, we start from at 0, 0, 2. We get pulled down into the xy plane. The next number I decided to do was 2, 0, 3. So that's 2 along the x-axis. So maybe if this was, I said that was 1. So this is 2 along the x-axis, 0 along the y, and 3 units up, 2, 3 along the z. So here I have my point 2, 0, 3. And when I plug it in, it leaves my first two coordinates untouched, and it zeroes out my third coordinate. So this one gets pulled down to here, 2, 0, 0. And again, it pulls this coordinate down to the xy plane. Last, I decided I should do something with a negative number in one of the first twos. So I have my 1, -2, -3. So again, I get 1, -2, and then 0. So let's do that. I hope you can see this in yellow. So I'm here at 1, x coordinate is 1, my y coordinate is here at -2. So this is where we are. This is actually my 1, -2, 0, but I have to go up 1 unit. This is my, oops, no, I have to go down 3, I'm sorry. 1, 2, 3. Somewhere around here is my 1, -2, -3. So in this case, this point gets pulled up to the xy plane. But what happens is all these points basically get reflected down into the xy plane, which is exactly what this is saying here. AX projects points in R3 onto the x1, x2 plane. In this case, I called x1 x, and x2 I called it y. So from 3 space, projected down onto a plane. And just to note, there are 2 things when I try to see geometrically what's going on. The 2 things I do is I plug in x1, x2, x3, and I try to see what's happening there. Sometimes, this one's not too hard to see, but sometimes it's a little harder. And so one of the things I do to augment that is then choose some points that I plug in and I graph it, and I take a look and use these 2 things. I combine these 2 things to try to give me a feel for what's going on geometrically. This next matrix, A equals 1, 0, 2, 1, is a shear transformation. And this is another transformation you want to kind of be familiar with, where you have ones at the diagonal and possibly some, what is the scaling factor on the off diagonals. So if T of x equals AX, where A is this 1, 0, 2, 1 matrix, acts on a 2 by 2 square, as shown, which I didn't draw it yet, then the set of images forms a sheared parallelogram. So here's that transformation. It takes a square and it makes this kind of parallelogram that's what they call sheared, kind of pushed over. And the way we're going to kind of analyze this is we're going to use the fact that because this is a linear map, the map Tx maps line segments onto line segments. So that means we can just analyze what happens to the four corners, and from the four corners we can draw our line segments. And that's exactly how I went from this square to this square here. I plugged in the corners. The first corner I plugged in on this square was the point 0, 0. So I'm going to just mark it in yellow to say that we're doing this one next. So I plug in 0, 0, I multiply by the matrix, and I get 0, 0. So it leaves this right where it is. So I'll mark that point 0, 0 in yellow. So this transform maps 0, 0 to 0, 0. The next point I'm going to do is this 2, 0 right over here. And when we do the matrix multiplication, it leaves it at 2, 0. So I'm going to maybe make this green. This green 2, 0, it just gets mapped right back to 2, 0. So next I'm going to look at 0, 2. So I'm going to plug 0, 2 in, and what I get is 4, 2. So this point here gets mapped over to 4, 2. And finally, I have my point 2, 2. This far off corner here gets mapped to 6, 2, which is over here. I guess I'll have to do this in red, which looks dangerous to me. Okay, there we go. So that's how we've mapped the corners, and because line segments map to line segments, this is a line segment, so we can just go from the yellow to the blue to get that line segment. There's a line segment from the yellow to the green, so I can draw that line segment, green to red, and then blue to red. So I have my transformation. I wanted to do one more square. So I picked this square here, and I started with the transformation of 1, 1, so this corner. And what I got when I multiplied by the matrix was 3, 1. So that came over here. And then the next corner I did was 3, 1 over here. I plugged that in, and I got the vector 5, 1 over here. So this blue point goes to this point. I don't have the same colors that I used last time, but that's okay. And then what do I have over here? I have the point 1, 3, and that goes over to 7, 3. So I haven't used green yet. So this one maps over to this point. And finally, I mapped 3, 3, and that goes over to 9, 3. So my 3, 3 gets mapped to 9, 3. So initially I was going to say, oh, the shear transform seems to keep the base and just moves the top up and over. But that's not quite accurate, because here it didn't really keep the base. It kept the length of the base, right? It's still length is 2, but it did move the base over. And then here it didn't move the top up, but it sure did shift it over. So I'm just going to plug in the variable x1, x2 to kind of get a better feel algebraically what's going on. So here I plugged in just generically x1, x2, and what I see here is for the first coordinate, which we plot on the x-axis, will be x1 plus 2x2, so it's definitely shifted over. And on the bottom, what we have is we keep our x2 coordinate, so x2 will stay. I'm just going to look to see that that's what I see when I plugged points in. When I plugged in 0, my x2 stayed. When I had a 2 here, that one stayed. Over here, definitely the x2 stayed. So my y-axis stayed the same, or my height of my bottom number always stayed the same. And then here you can see what we have is a change. x1 both gets a shift, a scale, and a shift over by x2 units. So we've talked about matrix transformations, and we saw these two examples, both this projecting points of R3 onto a plane, as well as this one here. No, not this one. Where is the shear? This one, the shear transformation. Next, we're going to talk about linear transformations. And the thing about linear transformations is they preserve the operations of vector addition and scalar multiplication. So we'll define what a linear transformation is, but remember, the idea is that it preserves vector addition and scalar multiplication. So a transformation or mapping, T, is linear if, 1, when you take the transformation of the sum of two vectors, that's the same thing as taking the sum of the transformation of the two vectors. In other words, T of u plus v equals T of u plus T of v for all u and v in the domain of T. 2. The transformation of a scalar times the vector is equal to the scalar times the transformation of the vector, or T of Cu is equal to C Tu for all scalar C and all u in the domain of T. So again, it's the idea that it preserves addition and scalar multiplication, so it kind of behaves in a nice way, not some unexpected way. So every matrix transformation is a linear transformation. And we saw that when we looked at matrix multiplication, that A of u plus v is equal to AU plus AV, and ACU is equal to CAU. And here's that statement again. Linear transformations preserve the operations of vector addition and scalar multiplication. But I'm going to do a quick proof for 2 by 2 matrices of this that matrix multiplication is linear. And the first thing I need to show is that T of u plus v is equal to T of u plus T of v. So for a 2 by 2 matrix, we're going to let A equal A11, A12, A21, A22 times u is equal to U1, U2, and v is V1, V2. So A of u plus v, so first I add my u plus v, so I have my matrix A times U1 plus V1, U2 plus V2. So when I do my matrix multiplication, I have A11 times my first coordinate, which is U1 plus V1, and A12 times my second coordinate, which is U2 plus V2. For my second coordinate here, my result, I'm going to have my second row times my column. So A21 is going to be multiplied by U1 plus V1, plus A22 times U2 plus V2. Now, everything in here now are scalars. A11, A12, A21, A22, those are scalars, and U1 and V1 are scalars. So now I can just use my normal algebraic properties of real numbers. So I'm going to go ahead and multiply this out. So I have A11 U1 plus A11 V1. I'll multiply this out. I have A12 U2 plus A12 V2. Similarly, for the bottom, I'll get A21 U1 plus A21 V1 and A22 U2 plus A22 V2. And now again, these are still all real numbers. So I'm going to group my U terms together, and I'm going to group my V terms together. So I'm going to group my A11 U1 plus A12 U2. Then I group my V terms, A11 V1 and A12 V2 here. I do the same thing for the thing below, the second row. So A21 U1 plus A22 U2. These are these two U. And then A21 V1 plus A22 V2. These are these two terms. So what you see is this here then. I can separate these out because this is by vector addition. I can separate this as one vector, A11 U1 plus A12 U2 and A21 U1 plus A22 U2. And I can add that to the second vector, A11 V1 plus A12 V2, A21 V1 plus A22 V2. Again, this is just by vector addition. And this here, by definition, is just A times the vector U, and this is the vector A times the vector V. I'm sorry, the matrix A times the vector V. So I have proven this first line that you need to prove for linearity. So the second condition is T of Cu is equal to Ct of u, and this one goes even faster. Oh, and by the way, I just kind of multiplied Au out. I don't know why, just to show that this last step was valid. Anyway, so Tcu equals Ctu. So A, because our transformation is represented by the matrix, A of Cu is equal to A times C times U1 Cu2. Now I do my matrix vector multiplication. So I have A11 times Cu1 plus A12 Cu2. And for my second entry, I have A21 times Cu1 plus A22 times Cu2. And again, these are now all real numbers in here, so I can move them around. So in particular, I can factor out my C. So I get C A11 U1 plus A12 U2 and C A21 U1 plus A22 U2. So I can take this C out because it's a scalar. And when you multiply a scalar times a matrix, this is how it works. And then from here, I have C times AU. So that proves the second property So we've shown that matrix multiplication is a linear transformation. Two more facts about linear transformations. The first one being t of the zero vector equals 0. The proof of this is pretty quick. So we're going to assume t is linear, and we're going to show that t of the zero vector equals 0. So t of 0 is equal to, well, we can make the 0 vector from 0 times any vector u. Then because it's linear, we can factor out the 0. And then this is just going to be 0 times some vector, whatever t of u becomes. It's some vector v, say, then 0 times v will give us the 0 vector. This second statement here about linear transformations, t of cu plus dv is equal to ctu plus dtv, where c and d are scalars and u and v are vectors in the domain t. And we have this generalization to go from just two vectors u and v to an arbitrary number of vectors p. So t of c1v1 plus c2v2 up to cpvp is equal to c1, taking out the scalar, tv1 plus c2 tv2 up to cp tvp. In engineering, this is known as the principle of superposition, that whenever an input is expressed as a linear combination of signals, so if v1, v2, vp are signals and our input is a linear combination of a set of signals, then the response is the same linear combination of the responses to the individual signals. In other words, you can figure out the response to the individual signals, multiply by the scalars, and then add them all together. For our example about linear transformations, we have given a scalar r. Define the transformation from R2 to R2 by t of x is equal to r times x. T is called a contraction when r is between 0 and 1, and a dilation when r is greater than 1. Let r equals 3 show that t is linear. And what we are going to use is this property here. And this is a one-way statement, or it's written as a one-way statement, but this one goes the other way as well. So if we can prove this property 2, then we have shown that t is linear. So we're going to show that t of cu plus tv is equal to c of tu plus 3 of tv. And we're going to plug in our definition of t over here, which is 3 times x. So t of cu plus dv is going to be 3 times our vector cu plus dv. And that, again, we're just plugging in the definition of t. But what we can do is we can use this algebraic property of Rn, and this is from a previous video, it's property number 5, that if we have a constant times the addition of two vectors, we can kind of do that distributive law, so it could be cu plus cv. So here we have 3 times cu plus dv, so we can distribute. We can make this 3 times cu plus 3 times tv. And now we use another algebraic property, whereas if we have two constants times a vector u, we can multiply the constants together first, and then we can also switch the order of the constants. So that's exactly what I did. I switched the order of the constants. And just a note, the switching of constants, this wasn't in the algebraic properties that were listed, but once you have CD, C and D are just real numbers, so you can switch their order, and then you can use this rule to make it, to put in the parentheses. So this is what I have with this property. But this here is simply Tu, and this here is simply Tv. So I have shown that T of Cu plus dV is equal to Ctu plus dTv. And therefore, I have shown that T is linear. Our next example is to define a linear transformation T from R2 to R2 by T of x is equal to 0, 1, minus 1, 0, times x1, x2 equals minus x2, x1. We want to find the images u of 4, 1, v, 2, 3, and u plus v, which is equal to 4 plus 2, which is 6, 1 plus 3, which is 4. So this is fairly straightforward. T of 4, 1, T of u is equal to 0, 1, negative 1, 0 times 4, 1, and that's equal to negative 1, 4. T of 2, 3 is equal to our matrix A times V, which is 2, 3, which is equal to negative 3, 2. And we kind of knew, like I did the matrix multiplication out, but we kind of also knew that from here because that was in the definition and you can verify it. You can multiply 0 times x1 minus x2 gives you minus x2, and then you have x1. You could have just plugged in my minus x2 and x1. So right here, minus x2 would be minus 4, and then my x1 for my second coordinate. Same here, minus x2 for my first coordinate, and then my x1 for my second coordinate. Now when I do t of 6, 4, I can multiply my matrix times 6, 4, and I get negative 4, 6. Again, I could have just plugged that in. And also, I can verify, because it's linear, I can verify that as negative 1 plus negative 3, which is negative 4, and 4 plus 2, which is 6. And again, we already knew that this was going to be true, that is t of 4, 1 plus t of 2, 3, because it's linear, but we just verified it. And we also know it's linear because it's represented by a matrix. And remember, we found that matrix transformations are linear. We proved that a couple of examples ago. Now let's take a look at this transformation geometrically. I plugged in my 4, 1 over here, and then what we saw is we got negative 1, 4, which is this vector here. So it essentially rotated this vector by 90 degrees. Similarly, my vector 2, 3 resulted in negative 3, 2. So that also rotated my vector. You can also see because they have the same, that their lengths are going to be the same because the 4, 1 has the same length as negative 1, 4. Similarly, 2, 3 is going to have the same length as negative 3, 2 because of the distance formula, the Euclidean distance formula using square root of x squared plus y squared. Anyway, so this transformation essentially becomes a counterclockwise rotation about the origin through 90 degrees. So something like this, where you have zeros along the diagonal and then something with negatives on the off diagonal, or ones, because if there's you could still have rotations if they're twos or other numbers other than ones, but those ones means it's not scaled. It preserves the length, and then the negative ones kind of start to give you different rotations. So rotations look something like this, and that's a good thing to remember. It's your basic form of transformation. Zeros on the diagonal, and then maybe something negative on the off diagonal. Here's another more wordy example, but not nearly as complicated. So a company manufactures two products B and C. For $1 worth of product B, the company spends 45 cents on materials, 25 cents on labor, and 15 cents on overhead. We saw a problem like this earlier in, I don't know, chapter something earlier. Okay, for $1 worth of product C, the company spends 40 cents on materials, 30 cents in labor, and 15 cents on overhead. We can construct a unit cost matrix, U, I guess for unit, equals BC, where B is the column describing the cost per dollar of output for product B, and C is the cost per dollar of output for product C. So here's product B, here's product C. Our costs are 0.45 and 0.4 for materials, 0.25 and 0.3 for labor, 0.15 and 0.15, both of them for overhead. Is that true? Both of them? Yeah, I guess both of them are 0.15 for overhead. So let X be a production vector corresponding to X1 of product B and X2 of product C. So now when we multiply X1 times our column B plus X2 times column C, that's going to give us the total cost of materials and total cost of labor and total cost of overhead. So the mapping T transforms a list of production quantities measured in dollars into a list of total costs. The linearity of this mapping is reflected in two ways. One, if production is increased by a factor, say 4 from X to 4X, then the cost will increase by the same factor from TX to 4TX, again because it's linear. And if X and Y are production vectors, then the total cost vector associated with the combined production X plus Y is precisely the sum of the cost vectors Tx and Ty, again because it's linear. So now we've finished the main material for our video. I have another, I think, 3 problems for you, but these problems you really should be able to do on your own. So I will give you answers, but I encourage you to pause the video after the problem statement, each problem statement, and try it on your own or give it some thought before you listen to the solution. I have a few definitions here for your reference. So for the first problem, suppose T is a transformation from R5 to R2, and T can be represented by a matrix. So T is equal to AX for some matrix A, and for all X in R5. How many rows and columns does A have? This kind of reminds me of a drawing I did for one of the examples earlier, but give it a try. So this is how I would approach this problem. First, I'm going to say I have a matrix A times a column vector X. And we are given that our column vector X, it's in R5. So we have X1, X2, X3, X4, X5, right? So because all X's are in X5. So that's going to tell us something. Since we multiply the rows of A times the column X, that tells us something about the length of the row of A. In particular, the row of A has to have 5 elements to multiply by x1, x2, x3, x4, x5, right? We're going to have A11, x1, A12, x2, A13, x3, A14, x4, and A15, x5. So we're going to have 5 columns. Now we need to know how many rows we need so that our final answer has R2. Well, if I look at this, and I really should have written this out, this is A11 x1 plus A12 x2 plus A13 x3 plus A14 x4 plus A15 x5. So that gives us 1 row. And we want to have 2 rows because this is it should be an R2. So that means we need 1 more row over here. So we're going to have 2 rows in A and 5 columns. So A is going to be rows, columns, 2 by 5. Our next example, let A equal 1, 0, 0, negative 1. Give a geometric description of the transformation. You know, I looked at this, and this looks like some sort of rotation. So I tried A11, which I have written here, or graphed out here, A11. And what I get is 1, negative 1. So this could be a clockwise rotation by 90 degrees. But I thought I'd better try 1 or 2 more vectors. In other words, especially ones with zeros for x or 0 for y. So I tried A10. And what I got is 1, 0, which is the same thing as what I started with. So it's not quite rotating everything. That's in blue, my non-rotated vector. So that was a little surprising, but remember what I told you, there are 2 things I often do when I'm trying to figure out a geometric description. First, I plug in some points. The other thing is I just plug in x1, x2, like a generic vector. And then instead of calling my variables x1, x2, I called it x and y. So I plugged in a 2-dimensional vector, a generic vector xy, and then I multiplied by my matrix A times x, and what I saw is I get x negative y. So what I have is a special type of rotation, which is a reflection across the x-axis, and it was spelled out for me once I plugged in my xy. And this is the last problem. The line segment from 0 to a vector u is a set of points of the form tu, and we had discussed this when we talked about parameterizing a line. So where t goes between 0 and 1. Show that a linear transformation maps this line segment, tu, into the segment between 0 and t of u. This is a transformation of u as opposed to little t, which is our parameter. This one's a pretty short problem. So t of tu, where this is little t, the parameter t, going between 0 and 1, we can pull out the t times tu because t is linear. We can pull out the scalar. But t of tu is a point on the line segment between 0 and tu, right? Because t goes between 0 and 1. So that wraps up those examples. We'll do a quick review, which is that we talked about linear transformation. So we viewed Ax equals b as a mapping or a transformation that takes a vector in Rn, if A is a m by n matrix, it takes a vector in Rn and gives us a vector in Rm. And from this point of view, solving the equation Ax equals b amounts to finding all vectors in X that are transformed to b. We said that a transform or function or mapping from Rn to Rm is a rule that it assigns each vector x in Rn a vector t of x in Rm. The set Rn is called the domain, Rm is called the codomain, and then we have this notation, t goes from Rn to Rm. And we also said for every x in Rn, t of x in Rm is called the image of x, and the set of all images is called the range. And then we talked in particular, this is just a general definition of transformation, but we looked in this video at matrix transformations in particular. And so we said that we would represent that this transformation could be computed by multiplying our vector x by a matrix A. And so again, now for an m by n matrix, we're taking vectors in Rn and mapping them to Rm, and we had some examples. And then what we said about matrix transformations is they turn out to be linear transformations. In other words, they preserve operations of vector addition and scalar multiplication, and these are the two properties that make something linear. So by definition, if you want to prove something's linear, you have to show these two properties hold. T of u plus v is equal to T of u plus T of v, and T of cu is equal to C tu, where C is a constant, a scalar. And then we found these other properties of linear transformations. Linear transformations takes the zero vectors and always maps it to zero. And also T of cu plus dv is equal to ctu plus dtv, where c and d are scalars. And this, we can also use this statement to prove something is linear. And then there was this generalization. Instead of just two vectors, we could take p vectors. So T of C1 V1 plus C2 V2 plus CP VP equals C1 T of V1 plus C2 T of V2 up to C of P T VP. And this is known as the superposition principle. So whenever we have an input expressed as a linear combination of signals, so our signals are the vectors V1 through VP. So we have input expressed as a linear combination of signals V1, V2 up to VP. Then the response, what comes out of T, is the same linear combination of the responses to the individual signals. In other words, we could just take T of each individual signals, multiply by the scalars, and then add them all up. Last, I have these examples here that we had gone through in the video, and I said these were some important examples to kind of know what the form looks like, to be familiar with. The two strategies to see what the graphical interpretation of a transformation is: one, just plug some points in and see what you get, and two, just plug in a generic point x, a vector x, and see what you get. And some of the basic transformations are projections from R3 onto a plane. We had rotations about the origin. We had translations, that is dilation and contractions. We had reflections across the x-axis, and then we had the shear transformation. And that's it for our review, and that's it for this video. Thank you for watching.